Hello again. Let's look at some more examples, particularly of the product rule. The derivative of x times the natural log of x. And some math textbooks, they won't bother putting this technically superfluous times sign here. They'll just delete the times sign, and which is perfectly okay. And well, if my computer will allow me to do so. It's been quite difficult right now. But anyway, let me just forget the whole thing. It's not going to let me do it. So the derivative with respect to x of x times the natural log of x, that's going to be by the product rule, f g prime plus f prime g. So I do x times the derivative of the natural log plus the natural log times the derivative of x on this other part. Now guys, remember the derivative of the natural log we stated without proof, that's just 1 over x. You'll just have to take my word for it. So that's 1 over x. And now the derivative of x is just 1. But 1 times natural log is just itself the natural log here. Okay. So I have, but now x times 1 over x is going to wind up being 1, which is kind of strange. Well, that's not strange. It's just kind of strange how this whole thing turned out. So we get 1 plus the natural log of x. Okay. So the derivative of x natural log of x is 1 plus the natural log of x. Okay. And now if we do the derivative of, let's say, x squared times the natural log of x, that would just be in a similar fashion. X squared times the derivative of the natural log plus the natural log times the derivative of x squared. Now again, x squared times the derivative of the natural log is 1 over x. And then now plus the natural log times the derivative of x squared, which is just 2x. So I have x squared. Now this x squared and 1 over x, that's just going to make x. So I have x plus 2x natural log x. And I wish I could get rid of these superfluous times signs. And let me do what I was trying to do 5 minutes ago. Okay. And I wonder if I could get rid of this one. Actually, I can. I mean, mathematically, there's nothing. Because, guys, time signs are understood, right? You can have them. It's okay to have these time signs. There's nothing wrong with them. It's just they're superfluous. That's not true of plus and minus signs, though, right? That's just true of time signs. So I have that. Okay, so there we go. And let me, just for neatness, let me skip a line here. It'll take just a second, but I don't like to have my stuff jingled. I like it all on the same line. Okay, so the derivative of x squared natural log x, that's x squared times the derivative of the natural log plus the natural log times the derivative of x squared. So it's x squared times 1 over x, because 1 over x is the derivative of the natural log. And then plus the natural log times the derivative of x squared, that's just 2x. And again, let me get rid of this superficial times sign. And so this times this plus this times this. But x squared times 1 over x, that's just x. So x plus 2x natural log x. And I can factor out x, and that's just x times entity in parentheses. I use brackets, you can use parentheses or whatever. 1 plus 2 times the natural log of x. And so that's that for that. Now the derivative with respect to x of, let's say, x squared times the x to the ninth, times the natural log of x. So that's going to be x to the ninth times the derivative of the natural log plus the natural log times the derivative of x to the ninth. And again, I'm going to skip a line like I did before. And again, these time signs are superficial. I can delete them. I might delete them here in a minute. You can keep them if you like. They're superficial either way. Oops, I didn't mean to do that. Oops, what did it do? Sorry. Something happened to my space bar there. My bad. So what I have is let's see, x to the ninth times the derivative of the natural log, which is 1 over x. And then I have the natural log times the derivative of x to the ninth. That's 9x to the eighth. Okay, but hey guys, x to the ninth times 1 over x, that's just x to the eighth. Oops, I messed up, didn't I? Oops. My bad. Sorry. Big mistake. That's x to the eighth. And now the second guy is correct. But you know what? That's going to mess up this guy over here. If I take out x to the eighth, that's not going to be x. That's going to be 1. Sorry about that, guys. I got really clumsy there. And then let me save that. Clumsy. So there's that. No, that was a mistake. That was not superfluous. That was actually a true mistake. So that's x to the eighth, not x to the ninth. Now what's the superfluous part is just these time signs, right? That's superfluous. This time sign right here is superfluous. It's not wrong. It's just we don't need them. They're an eyesore, if yes. So that's superfluous. And so is that. Let me create a space there just to make it easier to read, not because it's mathematically required. If I just put a space here, it just makes things a little easier to read. Do I need a space here? Maybe, yeah, just for readability, not because your professor would demand it. Okay, and so that's good. And let me get rid of this superfluous amount of sun here. Put a space just for neatness, no other reason. And in a similar vein, let me do that here. And I don't think I particularly need a space, but I'll do it anyway. Yeah, sure. No harm done. The spacing is not crucial. It's just for the sake of neatness, that's all. So here we are. And so again, to recap, the derivative of fg is fg prime plus gf prime. And then you just derivate these parts and you get this guy. Now, guys, something I need to talk to you about. Will your professor insist on you going from this step to this step? That depends on his or her taste. Technically, you're done right here. You could really stop here unless your professor wants you to filter out all terms. Really, in this kind of example, it's not really all that useful to do so, but just check with your professor. He or she may have a reason. Now, if you're dividing things and things cancel, yeah, you've got a reason. You've got a big reason. But here, that's not really happening. Okay. Let's see. Oops. Well, it went blank on me. Let's look down here. Let C be a positive and X be a positive. Then the natural log of Cx equals the natural log of C plus the natural log of X. That's by the rule. This is from Algebra 2, the logarithms. And so the derivative of the natural, but wait, the natural log of C is just a constant. So the derivative, but wait, the derivative of natural log of C plus natural log of X, that's just the derivative of the natural log of X, because this is just a dummy constant. It's just going to get killed in the derivative. So that's just the derivative of the natural log, which is 1 over X. Hence the derivative. So hence the derivative of ln Cx is just, or the derivative of ln Cx is just 1 over X. AKA the derivative of the natural log of Cx is just 1 over X. That C didn't make any difference. That's kind of cool. Now, that's not true for most functions in general. It's just true for the natural log. Don't get too used to this. It's good for the natural log, and you can get used to this for ln, but we can't get away with this for other functions in general, right? In fact, I don't know of any other functions where we can get away with this other than ln. Or perhaps possibly another log, but hold that thought. I'm not going to make any promises on that, but it's good for the natural log. A similar idea is true for any log type. The C doesn't matter. You know what? It is true for the other logs. Of course, if this was like the log 3, it would break up just like this, and the log 3 of C would get killed just the same. Now, you would have to do the derivative of the log 3, and you would wind up with something a little bit different, but we'll talk about that maybe later. But notice the C didn't matter. You'll get something different, but it's not on account of the C. So for any log, if the C is inside like this, it's superfluous. It's not going to. You may as well just derivate whatever log of just x instead of whatever log of cx. That C is not going to matter because it's going to get, as far as the derivative goes, it doesn't matter. I'm not saying it doesn't matter in any sense. I'm just saying it doesn't matter in the sense of the derivative, okay? So there's that. For example, the derivative of ln 7x is just 1 over x. Now do be careful. We didn't say anything about exponents, okay? The derivative of the ln of x to the 7th. Now remember, guys, you can bring that 7 out in front. Remember the ln of x to the 7th is 7 ln x. But remember, by the rules of derivatives, you can take that 7 all the way out. The derivative of 7 times something is just 7 times the derivative of that something. So we can take the 7 out even further, all the way out. And this time sign is actually superficial, so we just have 7 times the derivative of ln x. Now that's going to be 7 times 1 over x, which is 7 over x, okay? So there's that. Now let's look at this, the derivative of the natural log of sine x. Now this is going to be the chain rule. We're going to have to let u equal the sine of x. So that's going to be d by du of ln u times d by dx of sine x, my u term. And that's just going to be 1 over u for this part. If you derivate the ln u with respect to u, you get 1 over u. Derivate sine x with respect to x, you get cosine x. So that's just cosine x over u, but that's just cosine x over sine x, and that's the cot of x. After all, we were, u is sine x from the very beginning. Okay. So there's that. Now, the derivative of the natural log of the cosine of x, again, let u equal the cosine. You just get d by du of ln u times d by dx of the cosine of u. That's 1 over u times the negative sine of x. And I hated how it skips a line like that. That didn't happen to me up here, thankfully. It did happen down here. Yeah, I want my stuff together. Let me space. Sorry about that. I know this is annoying, but let me space like that. Now, guys, now this time sign here is actually, yeah, it's superficial. And you know what? This bracket doesn't even need to be there. I don't know why that bracket's there. Sorry about that, guys. Let me get this in better form. There we go. Okay, so we got 1 over u times the negative sine of u. No, not u, x. I'm getting all lopsided here. So I got 1 over u times the negative sine of x, because the derivative of the cosine of x with respect to x is the negative sine of x. Okay, you can just take the negative out to the side. That's sine x over u. So that's negative sine x over cosine x. That's negative tan x. Yeah, that's pretty cool. So what we've discovered is the derivative of the natural log of the cosine of x is the negative tan of x. And you know what? If you were to stick a negative in, if you were to negate both sides of this, the negation of this derivative would be the ordinary tan. Like if you stuck a negative sign right here, then you would get positive tan x. Okay. Now let's talk about what about other log types? What about the 10 log? This is understood to be log base 10. The derivative with respect to x of log base 10 of x. Now remember, by algebra 2, log base 10 of x is ln x over ln 10. So it's d by dx of ln x over ln 10. Now what you do is you factor out a constant. You factor out 1 over ln 10, and you just get d by dx of ln x. Oh, okay. Hey, that's just 1 over ln 10 times 1 over x. Now this times sign is needed. We kind of need this guy. And then that's equal to 1 over x times ln 10. Now this one's superficial. This one is really superficial, to be honest. And if you got rid of this times sign, you'd have to put parentheses around 1 over x. So I'm not going to do that. I could get rid of this one and put a little space there. Okay. But I'm just fussing over syntactic stuff at this point. So notice, guys, the derivative of log base 10 of x is 1 over x ln 10. Guys, if this would have been log base 3, the derivative of log base 3, you go through the same motions. It's just 1 over x ln 3. Instead of ln 10 down here, you got ln 3 down here. And you go through the same motions. You just got 1 over x ln 3. That's true. You can generalize this. If this would have been log 5, you'd had ln 5 down here. So on and so forth, okay? You know what? If this would have been log 1/3, you'd had ln 1/3 in here. You'd had 1/3. Excuse me. Back up. You'd had 1/3 inside this ln right here. Okay. But anyway, there's that. Well, technically, ln 1/3 is the negative of ln 3, but I don't want to get off on all that. But anyway, there's that. And here's another one that's kind of cool to do. The derivative of the tan of the ln of x. We let u equal ln x, so we got d by du of tan u times the derivative with respect to x of ln x. Ln x is my u term. So you derivate the tan. Remember, that's the secant squared. That's a good one to memorize, by the way. And then, so d by du of tan u is secant squared u times the derivative with respect to x of ln x is 1 over x. So d by du of tan u is secant squared u. D by dx of ln x is 1 over x. So, but hey, remember, we got to replace u with what it is, so we throw ln x back in the secant squared, so we got the secant squared of ln x over x. So there's that. And as far as superficial time signs, we kind of need this one if you're not going to do any parenthetical. We can get rid of this one. You know what? No, that's messy. This one is actually a good guy to have as well. Because we got some function times function going on. So let's just keep that around. So there's that. And I hope this is okay. So again, I did the chain rule, and I used the stuff I knew about the derivatives of natural logs and trig functions. Okay. So there's that. And I'll leave it for you to do this one right here, and this one right here, and this one right here for a homework exercise. I think that would be good to do. Real quick, let's look at the derivative of something like this. Let's say I've got the derivative of the sine 10 of x. Remember, that's just the sine of x quantity to the 10th power. This is what you think it ought to be. It's the sine of x to the 10th power. So we let u equal the sine of x, and so we got d by du of u to the 10th times d by dx of sine x. Again, this is just the chain rule. The 10 comes down, and then and we subtract 1, so we get 10 u to the 9th times d by dx of sine x. That's the cosine x. So we got, but remember, u is the sine x, so u to the 9th is sine x to the 9th, which is the sine 9 of x. That's just the definition thereof. Or the definition of the sine 9 of x is the sine of x to the 9th power, I should say. So we've got 10 times the sine of x to the 9th power times the cosine of x. And then in a similar fashion, if you just use tan instead of sine, you go through the same motions except u equals tan x. The idea is the same. D by du of u to the 10th times d by dx of the tan of x. Now remember, the derivative of the tan is the secant squared. So, and it does mean what you think it ought to mean. Secant squared of x is just secant x quantity squared. So we got 10 u to the 9th times the secant squared of x. You remember u is the tan, so it's 10 tan 9 of x, secant squared of x. And we're just going through the motions of the chain rule. That's all we're doing. And if you do cosine, you just got to watch out for the negatives. That's d by du, again, u10 times d by dx of the cosine of x. Now be careful, the derivative of the cosine is the negative sign, so you got to have a negative sign right here. So you got negative by SIGN, sine is in SIGN. You got a negative SIGN here. So it's negative 10 u to the 9th. Sine is in SINE right here, sine of x. So it's negative, now remember u is the cosine of x, so we got that u to the 9th is cosine 9 of x. And then you just plug, and there you go. And I'll leave it for you to do these for homework, this guy and this guy. And I think this video, I've got to end it pretty soon. Now, if I try to, what if I get slick if I put 3x inside here instead of x? Well, I've just got to do the chain rule. The bad news is I've got I'd have to do two things. I would have to let u equal the sine of 3x. Because now what's really going on here, guys, is we're taking the sine of 3x and we're raising it to the 10th power. So we got to let u equal the sine of 3x, but notice we still got a 3x inside here, so we got to let another guy, let's call him v as in Veronica, equals 3x. Now we had to deploy the chain rule twice. So let's see, what do we get? D by dx of sine 10 of, well no, it's back up here. Sorry, I was about to go to the next problem, my bad. So now what are we going to do? So we replace the sine 10, so we got d by du of u to the 10th, and then times d by dv of the sine of v, and then remember u is the sine of 3x, v is 3x, so we got d by du of u to the 10th times, again, d by dv of sine of v times d by dx of the innermost part, 3x. This 10 is the outermost part, the 3x, or no, the sine is the intermediate part, the 3x is the innermost part. Because what's going on here is this is really the sine of 3x all raised to the 10th power. The 10 is really the outsidemost guy. It just doesn't look that way. So you got d by du u to the 10th times d by dv sine v times d by dx of 3x. And you just do them. You do the derivatives. You'll get 10 u to the 9th. Derivate the sine term, you get cosine v. Derivate 3x, you just get 3 itself. Multiply that. Next thing is multiply that 10 and that 3. You'll get 30. And then you'll get your u to the 9th cosine v. But then just plug in the sine of 3x back in for u, and you get that. Guys, I got to stop the video. I'll pick this example back up on the next video. Bye.